Welcome back to the lecture. Let's do a recap of the last lecture. In the last lecture, we derived some statistical characteristics of correlator outputs, basically the mean and the variance of correlator outputs. So we have a signal transmitted, and a noise is getting added in between, and this is my observation in the receiver. Now I gave this x of t to the bank of correlators, and these are my correlator outputs. Output from correlators. Outputs from correlators. Now, what is the expectation of xj, that is correlator output? If I take one of the correlator output and calculate the expectation, what is that? It is nothing but Sij, where Sij is the signal component in that particular basis phi j, okay, and variance is n0/2. Now we know the basis functions are orthonormal, okay. So basis functions are orthonormal. Then we can prove that the correlator outputs xj's are mutually uncorrelated. That means if you take the covariance of any two, so actually this is the setup. We have x of t is given to the correlators. I have correlator here. Say I have phi 1 going here, phi 1 of t, phi 2 of t here, and like that. So I will get x1, x2, etc., x up to xn here. Now I take any two outputs from here, so correlator x1, x2, or any of them. I have taken xj and xk. So calculate the covariance. That will be equal to 0. That's what we call. That is what we say that correlator outputs are uncorrelated. Uncorrelated means covariance is 0. That is what we are going to prove next. So calculate the covariance of correlator output to take any two correlator outputs xj and xk. Now calculate the covariance. Expectation of xj minus mu xj, xk minus mu xk. What is covariance? Variance is expectation of x minus mu x the whole square. Covariance means, so covariance of xk and xj is expectation of xj minus mu, that is xj minus the expectation of this, that is mu xj, xj minus mu xj and xk minus mu xk. Now we know that xj is this. Xj is the correlator output, which is xij plus wj, that we have already seen. That means xj minus sij is wj. Okay. Similarly, xk minus sik will be wk. So we can replace this with wj and this with wk. So this is it. Now what is wj and wk? Wj is the noise component in the jth correlator output. That means it is integral 0 to t wj phi j t dt, and this is integral 0 to t phi u wu phi uk du. Okay. So this is the noise component in the jth correlator output, and this is the noise component in the kth correlator output. So simply you need to correlate that with its corresponding basis. Now we rearrange the integrals, collect the integrals in the left side, and collect the noise terms and the basis functions. Okay. Now we know expectation is a linear operator, so we can bring it inside this integral, and when you do that, this is the phi j and phi k are basis functions, which are deterministic functions. So expectation operate on these two. Okay, not on this. This will simply act as constant for expectation operator. So I have taken the expectation operator inside, so this will come outside of expectation operator, and w, t and w come here. So what is this? This is the autocorrelation function of WT. Autocorrelation function of WT. So what is autocorrelation? Autocorrelation is expectation of autocorrelation, or x of t comma u is nothing but expectation of x of t x of u. Okay, this is autocorrelation function. So here expectation of w of t wu means this is the autocorrelation function of w of t. So I have replaced that with autocorrelation function. Now what's the autocorrelation function of noise time that we have already seen in our first module? Autocorrelation function of white noise is n0 by 2 del of t minus u. So I replaced that with the autocorrelation function of white Gaussian noise. Okay. Now simply rearrange the integral once again. So n0 by 2. So I have taken this n0 by 2 outside, and phi k and its integral here, and phi jt and del of t together dt du. Now we know the shifting property of delta functions, that is integral x of t del of t minus t0 is equal to x of t0. So here integral phi of t del of t minus u means this will become phi j of u. Okay, now you have this all integral replaced with phi j of u. Now this is equal to n0 by 2 integral phi ku phi ju du. See, this is the inner product between, what is this? This is the inner product between phi k and phi j. Since they are orthogonal, inner product will be 0. So this is equal to 0. So what is this? Covariance of xk and xj, which is equal to 0. That means xk and xj are uncorrelated. Now uncorrelatedness implies independence in the case of Gaussian random variables. Okay, specifically for Gaussian random variables, uncorrelated means independence. That means if two Gaussian random variables are uncorrelated, they are independent to each other. Okay. Now what is independence? If A and B are two independent events, probability of A intersection B is equal to probability of A into probability of B. Okay. Now if two random variables x1 and x2 are independent, then what is their joint probability density function? F of x1 x2 is equal to fx1 of x and fx2 of just product of their individual PDFs. The joint PDF is the product of their individual PDF. That is when two random variables are independent. Now here we have said that the correlator outputs are uncorrelated, and which also implies the independent. That means the correlator outputs are independent, because we have assumed AWGN channel means additive white Gaussian noise channel. So the correlator outputs are Gaussian distributed, they are uncorrelated means they are independent. Now this is the observation vector. Okay, this is the correlator vector which represents the correlator output x1 x2 etc. This is the vector which consists of the correlator output x1 up to xn. So this is the observation vector. Now we have seen that correlator outputs are independent. If the correlator outputs are independent, what is the joint PDF of x case? Okay, so if you take the joint PDF of these n random variables, that is fx1 x2 etc xn, okay, this is the product of their individual PDFs, because x1 up to xn are independent. Okay, or the PDF of this observation vector, which is the joint PDF of its components. Okay, so PDF of this observation vector is simply the product of their PDF of their individual elements. Now for AWGN channel, what is the expectation of AWGN means Gaussian distributed. So Gaussian distribution is characterized by the mean and variance. Now what is the mean of a correlator output? So I take a correlator output xk. What's the mean of that? This is sik. What's the variance of that? Which is n0 by 2. Now what is the PDF of a particular correlator output fxk? So that is, so we know the Gaussian distribution PDF. So this is the Gaussian distribution PDF. Okay, what is that? Gaussian distributed fx of x 1 by 2 pi root 2 pi sigma square expectation of x minus mu all square by 2 sigma square. Now what we need to do is replace sigma with n0 by 2 and mu by sik for this particular PDF. Okay, an example, x is distributed with mean 1 and variance 2. Then what we have to do, I need to substitute 1 for mean, so this, and 2 for variance here, and 2 into sigma square, 2 into 2 4, right? Okay, so similarly I have replaced the variance and mean here. Okay, so variance is n0 by 2, so I have put n0 by 2 here and mean here. Okay, and I get this expression. So this is for a single correlator output. So this is for correlator output xk. If I am taking x1, I need to replace this with si1. If I am taking x2, I need to replace this with si2, k with 2. That's all. So if I am taking kth correlator output, I represent it with sik. Now what will be the joint PDF of, or the PDF of the observation vector? It will be the product of individual PDFs. So I simply replace k with 1 here, again k with 2 here, similarly up to n. Okay, the product of n correlator outputs. Now we know we have this term n times multiplied, so 1 by root 2 pi n 0 power n, and this is the product of exponents. Product of exponents is exponent summation of that this term, exponent term, right? So we will be getting this term. Okay, you can simply work it out. So this is the PDF of the observation vector. Now we have derived the PDF of the observation vector fx of x, right? This is the PDF of the observation vector, but it is actually dependent on Sij, right? For different Sijs, this observation vector will be different, right? So this is actually dependent on, this PDF is actually dependent on Sij. As I have said earlier, this is the PDF of a random variable x. Now I say the random variable x is distributed with mean 1 and variance 2. Means this is the PDF of that particular random variable. Now if I say another random variable y is distributed with mean 3 and variance 1, then I need to replace mean and variance here. That will be a different distribution. Here we have variance constant for all the random variables, but mean is dependent on the signal vector. Okay, now if we replace Sij, for example, if I have the signal Si, if I take signal S1, then it will have a particular PDF. If I take the signal S2, it will have a different PDF, right? So it is dependent on Sij, means that this is actually a conditional PDF. Okay, so PDF of the vector x given the value Sij. Okay, PDF of the vector x given the value of Sij, or you can say PDF of x given the simple my, because Sij is actually dependent on mi, that we will actually discuss shortly. Okay, so that's it. Now let's move to the next topic, that is maximum likelihood decoding. See, take the example of particular digital communication system. How it will look like: I have a message to transmit, okay, M0 or M1. These are called symbols. So for example, 0 and 1, I may be transmitting 0 or I may be transmitting 1, and in the receiver I may have to detect what I have transmitted, 0 or 1. Okay, I am transmitting in this simple case I am transmitting two informations, either 0 or 1, and I'll be detecting that 0 or 1 in the receiver. Receiver has to say whether I have transmitted 0 or 1. Now this 0 or 1 is represented by M0, M1. So these are called message symbols, or symbols, simply symbols. So in this case I have only two symbols. Generally we have M symbols transmitted. M0, M1 up to MM symbols will be transmitted from the transmitter, and in the receiver I may have to select one symbol from these M symbols and say that this was transmitted. And how we decode that is what we are going to discuss next. So I am transmitting symbols, and in the receiver itself I have an encoder which actually encodes these symbols to some analog signals. For example, if I transmit 0, I will be sending an analog signal S of t, and if I transmit 1, I will be sending another analog signal S1 of t. Okay, for message symbol M0, I will be transmitting an analog signal S0. For symbol M1, I will be transmitting an analog signal S1. Now this S0 or S1 is going to the channel where some noise is getting added, and I have this. So Si is nothing but S0 or S1, and I receive that in the receiver. Now in the generic setting, okay, I have M symbols to transmit, so it will be encoded to M analog signals, S1, S2, etc. up to SM, and in the channel a noise will be getting added, and I will be receiving this. Okay, this is observed signal. Okay, now the question is how to detect Si back, or how to determine which Si was transmitted. Okay, so I am in response to some message symbol, I will be transmitting an analog signal Si of t, and I will be receiving a completely different waveform X of t, because a noise is getting added in the channel. So I will be receiving X of t, and from this received X of t, I may have to tell which Si of t was actually transmitted, or which message symbol was actually transmitted. That is what we are going to discuss in maximum likelihood decoding. Suppose that in each time slot of duration t, one of the m possible message signals are transmitted. Okay, so M0, M1 or up to MM, or correspondingly S1, S2, etc. up to SM. So I have message symbols not from M0, M1, M2, etc. up to MM. Corresponding to that, I will be transmitting analog signals S1, S2, etc. up to SM. And we are assuming that they are transmitted with equal probability 1 by m. I have m symbols. So m1 m2 or sc s1 s2 etc. up to sm is transmitted in a time slot of duration t. So for first 0 to t seconds, I'll be transmitting some signal, say s2 of t, and for the second time slot I'll be transmitting, say, sm of t, like that. And each of it has equal probability to get transmitted, so that probability is 1 by m. This is to simplify our calculations. Now assume that we have n basis functions as well. Okay, so our basis functions are phi 1 up to phi n. This is my signal vector. Okay, signal vector, and this is my observation vector. And this is my noise vector. Right. For instance, let's assume a 3D picture of this. That means I have only 3 basis functions. Okay, phi 1, phi 2 and phi 3. We have assumed n basis functions. For example, we are assuming that I have only 3 basis functions. Then the signal vector will have 3 values. Okay, similarly the observation. Now this is the case. I have the basis phi 1, phi 2 and phi 3. So this SI will be some point here. Okay, some point. So this is the point SI. Okay, now what is X? X is nothing but SI added with the noise. Okay, SI added with the noise component. So this is my vector SI. Let's assume that this is my noise vector W. This is my noise vector W1, W2, W3. So this is getting added to my signal vector. Then the resultant X will be this. We know the triangular law of addition of vectors. Okay, so this vector added with this vector will give you this vector. So this is my received point, received signal. Will that be always? Will my received signal point will be at this point always? No, because the W is random. So W can be somewhere here. Then my received signal will be this plus this. So something like this. W can be here. Okay, W can be like this. W can be like this. Here W is in this direction. W can be in this direction. Then my received signal will be here. Okay, received signal will be here. If W is in this direction, my received signal will be here. Okay, so X will be here, which means that I am transmitting X and a random noise is getting added. Then my received signal will be in a cloud around this point, somewhere in the cloud around this point. That's what is depicted here. So I have transmitted my message signal SI, and the received signal will be somewhere in this cloud. Can be this point, it may be this point, maybe this point, this point, this point, or something. And the radius of this cloud may be determined by the length of the maximum energy of the noise. Okay, so let's leave that for the time being. Now this is the detection problem. So I am transmitting a signal, noise is getting added, and the received signal will be some point in a cloud around my transmitted signal, transmitted vector. Now how can we define? Now I need to get my received transmitted signal back from the observed signal. Now we can define our problem as this. Okay, So given an observation vector x, perform a mapping from x, that is my received vector. From this vector I need to do some kind of mapping, okay, so that I estimate m cap of the transmitted symbol my. Okay, my signal mi was transmitted and x was received. From x I need to find some estimate of mi. Why I say estimate? Because I may not be able to find exactly what mi was transmitted all the time. Okay, I am estimating, so I'm not saying that this is what exactly transmitted, but I have estimated it like this. So maybe if my detection algorithm is very good, maybe 99.99%, that may be what actually was transmitted. Okay, so I am doing a mapping from the observed vector to an estimate of the transmitted symbol in a way that would minimize the probability of error in the decision making process. So how should I map my observation vector to the estimate, or what should be the condition on the mapping? That is, the mapping should minimize error. Okay, so I am deciding that m1 was transmitted. Okay, but if actually m2 was transmitted, there is an error. Such kind of error should be avoided. Okay, that is the condition. So I have an observation vector. From the observation vector I am finding an estimate of the transmitted symbol in a way that it will minimize the probability of error. That is, in a way that the error in this decision making process is less. Okay, now given the observation vector x, suppose that I take a decision like mi was transmitted, then what is the probability of error in this decision? Let us denote it by probability of error, say PE, probability of error, in deciding in favor of the symbol mi given the observation vector x. I have received the observation vector x, and if I decide in favor of mi, what will be the probability of error? It is nothing but 1 minus probability of mi cent given x. That is, what is this? This is the probability that having received x, what is the probability that mi was transmitted? Okay, I have received the vector x, observation vector x, and what is the probability that this x was actually from mi? Now 1 minus this probability is nothing but probability that mi was not transmitted given x, which is actually the probability of error here, because I am deciding in favor of mi. Now what will be the probability that I have made a wrong decision? Okay, I am saying that mi was transmitted, but what is the probability that that decision was error if mi was not transmitted? Now what is the probability that mi was not transmitted? It will be 1 minus probability that mi was transmitted given x. Okay, now we need to actually minimize this probability of error. Means I need to maximize this probability, because this is 1 minus. If I maximize this part, it will minimize this part. That means I have m message symbols, m1, m2, etc. up to mm. in this, that particular mi for which this probability is maximum among all other mj's, j is not equal to I, will minimize this probability of error. That is, I have m symbols. Okay, suppose in this m2 has maximum probability. So for example, probability of m2 given x, probability of m2 given x is maximum among the probability of all other symbols. Then this will minimize this error. Then what should I do? I should take a decision in favor of m2. Okay, that is the basic logic here. For example, I have 4 message symbols transmitted. This is called alphabet. Okay, m array alphabet, m array alphabet. Okay, so I have 4 messages to transmit. Now I need to calculate probability of m1 sent given xi, that is, I have observed x observation vector, I have the observation vector. Now what will be the probability that it is from m1? What is the probability that it is from m2, m3 and m4? Now assume that m2, probability of m2 is maximum among all the other. Then I will estimate mi as m2. Now this is a decision rule. Set m cap is equal to mi if probability of mi sent x is greater than or equal to probability of mk sent x for all k's not k not equal to I. That is, I am finding this probability for all the message symbols, and if I is having maximum probability than all the others, okay, then decide in favor of that. And this is called maximum a posteriori probability map rule. Maximum a posteriori probability map rule. Okay. Now we have studied Bayes rule. That is Bayes rule. Probability of A given B is equal to probability of B given A, probability of A divided by probability of B. Okay, Bayes rule. Apply Bayes rule here. Probability of mi given, this is mi sends, I have simply skipped sent. Okay, probability of mi given x is equal to probability of x given mi, probability of mi, probability of x. Now we select the symbol mi which maximizes this. That is what we have seen above in the map rule. Or if I use Bayes theorem, I should select mi which maximizes this, because maximizing this will maximize this. Okay. Now in terms of conditional PDFs, okay, conditional PDFs and this particular equation, we can restate map rule as this. That is, so this part is in terms of probability. Now we are translating that in terms of probability distribution functions. Sorry, probability density functions. Okay. So I can write it like this: pi k fx x given mk. Okay, instead of p, I have simply translated that to ptf. Okay, where pi k is the probability of transmitting a symbol mk. So this same as this. Okay, so simply instead of I have used k. That's all. Okay, probability of mi, simply probability of mk. So pi k is nothing but the probability of mk, and this is called prior probability. Okay, prior probability of the symbol mk. So why it is called prior probability? Because this I know already. So what is, for example, if I toss a coin and say that it's a fair coin, I know that the probability of getting a head and tail is 0.5. So I know prior to the experiment itself the probability of getting a head or tail. So this is called prior probability. In this case, I know the prior probability of the symbol mk. This is 1 by m. We have assumed that they are equally likely. So prior probability, pi k is the prior probability. And in the previous case, we have when we discussed map rule, okay, here this is actually posterior probability. Okay, this is actually posterior probability. That is, here having received the vector x, what is the probability of mi? I have some information here, x. Now, having received that, what is the probability? What is the probability that it is sent from mi? So if I simply tell probability of mi, it will be 1 by m. But given x, that is, I have some more information, x. Now, what is the probability of mi? Okay. Now, this PDF is actually the conditional PDF of observation vector x given mk, and this is called likelihood function. Okay, likelihood function. That is like having transmitted mk, what's the probability of the vector x? And this is represented as L of mk. Okay, this is actually conditional PDF. For each mk, this PDF will be different. So this PDF is dependent on mk. So we have represented like this, L of mk. When we change mk, this L will have a different value. Okay, now in the previous equation, replace pi k with 1 by m. Okay, because it is of equal probability. And see, we are going to maximize this function, right? We are going to maximize this. So I need to find mk which maximizes this. That mk is actually transmitted. See, set m cap is equal to mi if this function is maximum for k equal to I. That is, if this function get maximized k equal to I, that is mi here, then I will say mi was transmitted. So I need to maximize this function with respect to mk. Now in the case of maximization, it is with respect to some function, okay, right? Some variable or some function. Now this pi k, it is a constant 1 by m, so I can simply remove that from the maximization process. As well as this is also is not dependent on mk. Okay, this is the probability density function of x, the vector x, and it does not have any dependency on mk, so we can remove that as well. Okay, now I can say that set m is equal to mi if this is maximum. That is, if this is maximum, the previous thing will be maximum. Okay, so maximum for k is equal to I. And or instead of this, I can replace it with likelihood function. Replace it with likelihood function. So I have rewritten that here. Now instead of likelihood function, we will be always working with log likelihood function. That is, take the natural logarithm of likelihood function, because it will be more easier to work with log likelihood function. And because of the property of log functions, its monotonically increasing property, the mk which maximizes this function, that is likelihood function, the same mk will maximize log likelihood function as well. Once again, the mk which maximizes this likelihood function will maximize the log likelihood function as well. And we are actually interested to find that mk, that is, which mk maximizes the likelihood function. I will decide in favor of that mk. I would say that that mk was transmitted. So I need to find the mk which maximizes. Here the mk which maximizes likelihood function maximizes log likelihood function as well. So I can simply work with log likelihood function instead of likelihood function. Now we decide the maximum likelihood decoding rule as this. Okay, set m cap is equal to mi if L of mk is maximum for k is equal to I. Now for AWGN channel, we know this is the likelihood function, that is the conditional PDF. We simply we derived it just before. This is L of mk. Now find the log likelihood function, find the natural logarithm, okay, ln of this. So when you find the ln of this exponent get cancelled, okay, exponent and ln will get cancelled. So we'll be left with some summation term. If I was supposed to work with likelihood function, I may have to work with this term, some exponent term. But here when I convert that to log likelihood function, it has converted simply to a summation. Now this term, it is a constant. See, n is a constant, okay, n0 is a constant, pi is a constant, all thing is a constant. Constant does not do anything in maximization. It does not have any effect in the maximization process, so we can simply drop this as well. So the log likelihood function is this. Okay, so the mk which maximizes this function, okay, decide in favor of that mk. But this function is maximum when this function is minimum, because I have a negative sign here. So the all thing is maximum when this thing is minimum. Now let Z denote the n-dimensional space of all possible observation vectors. For example, I have two basis functions, phi1 and phi2. Now the observation vector will be two-dimensional. Okay, observation vector will be two-dimensional, okay, somewhere in this plane. So this plane is called Z, the observation space. Okay, this is the observation space. Now let us partition that to m regions, namely Z1 and etc. to Zm. Here I have partitioned that to Z1 and Z2. Okay, now if x falls in Z1, I would say that m1 was transmitted, and if it is in Z2, m2 was transmitted, like that. That is, I have the observation space. Observation space is nothing but the space of all possible observation vectors. So I have the observation vector. It may have different values, okay, depending on the noise. So all possible values, such values is called observation space. Now I have partitioned that to m regions because I am transmitting m symbols. I have partitioned the observation space into m regions, and I would say that if my signal observation vector falls in the region Z1, I would say the message m1 was transmitted. If it in Z2, message m2 was transmitted, like that. Now the question is that how to partition this Z into Z1, Z2, etc. to Zm. Okay, if I properly partition that, the error will be 0 or error will be low. So for example, here I have two regions, Z1 and Z2. If my observation vector falls somewhere here, okay, above this region, this red region, I would say the symbol M1 was transmitted. If it falls here in the blue region, I would say M2 was transmitted. Now I would restate it as this. X lies in region Zi if the log likelihood function L of mk is maximum for k is equal to I. Once again, if I transmit M1, suppose I transmit M1, and this log likelihood function will be maximum for M1, okay, and then my X may be in the region Z1. Okay, we have partitioned our space into M regions. Okay, now I can say that based on my previous definitions, my observation vector X will lie in the region Z1 if this log likelihood function is maximum for k is equal to I. Okay, for example, if this log likelihood function is maximum for k is equal to I, my transmitted symbol was mi. If I have transmitted the symbol mi, where will be my observation vector X? It will be in the region Zi. Okay, once again, if my log likelihood function is maximum for k is equal to I, that means I have transmitted the symbol mi, which implies that my observation vector X would be in the region Zi. Again, I can replace this with log likelihood function of AWGN channel. So this, but this I have dropped the negative sign. Then instead of maximization, I would say minimum. Okay. Now let's take this log likelihood function, use a minus b all square here. So I expand it like this. So this is the energy of the vector X, observation vector X. Okay, energy of the observation vector X. For example, energy of a vector. Okay, I have a vector y is equal to y1, y2, y3. The energy of the vector is y1 square plus y2 square plus y3 square. This is the length of the vector, that is energy. Okay, so this is the energy of the observation vector X, and this is the inner product between the observation vector X and my signal vector xk. Okay, kth signal vector and observation vector, inner product between these two, and this is the energy of the signal vector xk. Okay, now this one does not play any role in the maximization because it is independent of the index k. Okay, actually we are finding which mk or which sk which minimizes this term, but this term doesn't have any role in that because it does not have the k index. Okay, so simply remove that. So we will be left with these two terms. So we need to minimize this. Okay, we need to minimize this. So I need to find the sk which minimizes this term -2 sigma xj skj sigma skj square. I need to find that skj which minimizes this term. Okay, or I can say if I multiply everything with a minus sign, this will become plus and this will become minus, and divide it by 2, then it will be sigma xj skj minus 1 by 2 this. I need to maximize that term. I need to minimize this term, or I need to maximize this term. So we will restate maximum likelihood rule for one last time. That is, the maximum likelihood rule is observation vector x lies in the region Zi if this summation or this expression is maximum for k is equal to I. Now, if the observation vector x lies in Zi, set m is equal to mi. So this is the maximum likelihood rule for AWGN channel. Now this is just a picture representation of the decision regions and decision boundaries, or observation space and observation regions. Okay, I have n is equal to 2, m is equal to 4. That is, I have 2 bases and 4 message points. So phi 1, phi 2, m2 up to m4. Say these are my message points. Okay, this is m1, this is m2, and this is m3, and this is m4. Now I have a decision boundary like this. Okay, this is my decision space, or of the observation space is that entire thing is this entire 2D plane is that observation space, and I have partitioned that into 4. This is Z1, this is Z2, Z3, and this is Z4. Now I say if my x falls somewhere here, okay, or here, or here, I would say that my transmitted signal was m1. Okay, if it falls somewhere here, I would say transmitted signal was m2, and m3, m4 likewise. Okay, all right. Now let's see an implementation of this maximum likelihood decoding. Okay, so this was my maximum likelihood decoding rule. Okay, so the receiver which implements maximum likelihood rule, or which uses maximum likelihood rule, is correlation receiver. Okay, so this is the maximum likelihood rule. I need to maximize this. Okay, and the k which maximizes this expression, okay, that the message symbol corresponding to that index is set to be, or is decided to be, transmitted. Once again, this is the decision rule. Okay, now this is a function of k, index k, so sk or k, ek. Okay, so the k which maximizes this, okay, find that k, find the message symbol corresponding to that k. If k is equal to 1, m1, k is equal to m2, and decide in favor of that message symbol. Okay, now this is correlation receiver. Right, I receive my signal here, x of t observation, signal observed, signal observed signal. I give that to an array of correlators, okay, bank of correlators. So here I will get my observation vector x1, x2, etc. up to xn. Now what I do, I should implement this equation. Okay, so this is my observation vector. Now this observation vector is given to here. This observation vector is given to here, and I need to maximize this term for k. Okay, I need to find the summation for every signal that I have transmitted. That is, S1, the signal S1 of t will give me the signal vector S1. Okay, that is S11, S12, etc. up to S1n. I have n basis function. Similarly, S2t will give me signal vector S2. Likewise, I have m signals getting transmitted for each message symbol, m1, m2, etc. up to mm. So Sm of m of t will give me the signal vector Sm. Now what is this? This is the inner product between my observation vector and signal vector. This is nothing but inner product between observation vector and signal vector Sk. Now I need to find for which k this is maximum. That is, I should find this summation for k is equal to 1. I should find this expression for k is equal to 2 for the first transmitted signal, or the first message symbol, for the second message symbol, and for mth message symbol. For all m message symbols, I need to calculate this expression and find which is maximum and decide in favor of that. That's what I am doing here. This is my S1, S2, etc. up to Sm. Okay, this is my first signal vector, second signal vector, third signal vector. Okay, I'll be multiplying them. This is an inner product calculator, that is, it gives the summation. Okay, I multiply them point wise. Okay, x1 with s1, x1 with s11, x2 with s12, x3 with s13, like that, sn with s1n. That is what this multiplier do. Then accumulate, that is sum them. This is summation. Accumulation is called nothing but this summation. So I multiply each term by term, then accumulate. That is x transpose s1. Okay, x transpose s1. This is the inner product between x and s1. I have calculated that. That is, this term is calculated. Similarly, for s2, I can calculate that term like that, for up to sm. Now I need to subtract energy of get signal vector. So E1 is subtracted from this, so note the negative sign here. Okay, so from this is getting subtracted. So I have this term here. Okay, 1 to n, that is this expression for k equal to 1, that is for the first symbol or first signal. Similarly, this is for the second signal, and this is for the nth signal. Now what this block do, it will select the largest input from this. Okay, it has m inputs, each for each symbol. Okay, now select the largest input, find the index of that input. If this is giving the largest value, then index is 1. If this is, then index is 2. If this is, index is m. So find the index corresponding to the largest value. Now decide in favor of the symbol which is having that index. Okay, so select the largest input from, find its index k and output mk is equal to mk. This is called correlation receiver. With this, we finishes the third module. Thank you.